finishing off with these two variable inequalities. What we did so far is list the first step. There's really only two steps to it, but they're pretty involved steps. First is to graph the corresponding linear equation. So if you're graphing a linear inequality, you pretend like it's a linear equation. So what I'm going to actually do is I'm going to graph y equals 1/3 x minus 2. Now, I have to keep in mind this little asterisk here. This asterisk means you got to be careful. Don't draw a solid line because it might be dashed, right? We have to watch out for that. Because what you're doing right now when you're graphing this, you're doing your dividing line. You're figuring out, okay, this is the dividing line between solutions and non-solutions. Right? So this is the border line that you're putting in here between when the inequality goes from solutions to not solutions or not solutions to solutions. So when we graph this, if it's in slope-intercept form, you're ready to go. Y-intercept here is 0, -2, and a slope of 1/3, that means up 1, right 3. Now, before I draw in a line, problem. That line, the border that I'm about ready to draw in, that's not included as part of my solutions. So what I have to do is I have to make this a dashed line. Somewhat straight there. Okay, so that's still separating my solutions from the solutions might be above, then the non-solutions would be below, or vice versa. Non-solutions might be above, then the solutions would have to be below. It's the dividing line, but what we're really saying here is any point on this line, that's not a solution to this inequality. But the solutions will lie up to just not including those. That's what we're saying with this dividing line. So that takes care of all of step 1. Graph the corresponding linear equation, solid dashed. In this case, it was dashed. All right, step 2 of the process. This is really the final step. This is the testing. Okay, so where are my solutions? Now, you don't need a ton of testing points. In fact, you just need one. One is going to tell you everything you need to know. What you're going to do is you're going to pick a point that's clearly above or below the line. Right? Basically, pick a point that you're sure is not on the line. Any point at all will do. I kind of prefer the origin when it's available. Now, if your line passes through the origin, you can't use the origin. I like the origin because the x is 0 and the y is 0. It's very easy to calculate when I put it into my inequality, but I'm going to test it back into this inequality. I mean, that's how you test whether the ordered pair is true or false, whether it's a solution or not a solution. So we'll just say pick a test point. Test point, and so as not to write a novel here, we'll say pick a test point and shade accordingly. Shade accordingly. All right, so we're going to pick a test point. Like I said, I'm kind of partial to the origin. It's easy to plug in and see. So I'm going to pick a test point. In this case, the origin works. As long as it's not on the line. It can't be on the line, and the origin is clearly above this line. So we're okay to use it as a test point. Now, I don't get upset if it's false, and I don't celebrate if it's true. All this is telling me is where my solutions are going to be, and I'm going to know whether it's true or false, right? From whether it's true or false. All right, so we put in 0 for the x, or for the y coordinate, sorry. It's not going to matter for the y and the x. Greater than 1/3 times 0 minus 2, and this is still a question mark. So we have to interpret this statement. So 0, we're saying, is greater than 1/3 times 0 is 0, minus 2 is -2. So look at the statement. Is 0 greater than -2? Yes, that is 100% true. What does that mean? It means that 0, 0 is a solution, as well as every other point that's on the same side of this borderline as 0, 0, which means 1, -1 is a solution. 5, 4 is a solution. 0, 4 is a solution. Every point that's on the same side of the line as this true point will also have to be a solution. So all I'm going to do is shade every point. In this case, that would be above the line. Why? Because the origin was the above the line and it worked. Now, had I got a false statement, it's like, got to try another one. No, that's not how it works. If it's false, all points on that side will be false, which means, by logic, all points on the opposite side must be true, and I would just shade the other way. You should never need more than one test point to figure out which way to shade. So all these ordered pairs that I have shaded in here are solutions to this inequality, right? Up to but not including the line itself, and the reason is, well, there's no equal to here. But we definitely need to graph the line in order to get that dividing border where our solutions go from true to false or false to true. All right, so let's try a couple others just to show you how these work. Again, it comes back to how well you can handle the equations, the linear equations. The inequality is just one extra little hurdle you got to get through. All right, so I have 2x plus 3y. 2x plus 3y is greater than or equal to 6. All right, so call this the second example. Okay, well, step one of the process. Step one is I plan on graphing 2x plus 3y equals 6. I'm going to graph the actual equation. Right? Now, graphing this requires, well, I'm going to put it in slope-intercept form because that's how we've been graphing our lines up to this point. So if we subtract 2x, we're solving this for the y variable. And we divide everything by 3. That puts us at negative 2/3 x plus 2. Now, what some people will do is they'll bring the inequality down. Don't do that. I'm not doing anything with the inequality because sometimes when you solve for the y variable, you have to divide by a negative, and you're going to have to remember to reverse the inequality. It's just best to test it back in the original and not bring that inequality down. The only point of this is to just get the borderline. That's all I need it for. Right? I'm not testing which way I shade. I'll test that once I get the border drawn. So I'm looking at y equals negative 2/3 x plus 2. That's slope-intercept form. So positive 2 is my y-intercept. From there, I need to go down to right 3. Remember, that's a negative 2 over a positive 3. Or you could go up to left 3. That would be a positive 2, negative 3. Now, in this particular problem, I know that this is a solid line. The reason I know it's solid, that equal to right there. Right? So that means points on the border are actual solutions. So is this point at 3, 0 a solution to this inequality? 100% yes. I guarantee it is. If it's on this line, it's a solution because the line is solid. It's included in my solution. All right, so as far as testing points, well, if the origin's available, I'm going to use it. And it is. As long as it's not on the line, it's a decent testing point. So 0 for x, 0 for y, go back to the original. So we have 2 times 0 plus 3 times 0 is greater than or equal to 6. That's the question. And what do you get? Well, you get 0 is greater than or equal to 6. This time that's a false statement. Not a big deal. Okay, so it's false. That means 0, 0 doesn't work as a solution, and neither will any other point that's on the same side of the line as 0, 0 is, which means all the points below because 0, 0 is below. Therefore, process, little logic here, I guess. All points on the opposite side must be solutions to this inequality. Right? Okay, this last example I want to show is sometimes, particularly on that knowledge assessment, which, we're trying to pass here, sometimes they'll just graph a linear inequality. So you might get something that looks like this. Let's put a dot there. Dot here. Draw this. And what they would ask is they would say, okay, what linear inequality is represented by this graph? In other words, write the linear inequality that's represented by this graph. Well, first things first. We got to figure out what this border line is. What's the equation of this line? Well, this goes back to how we write linear equations. Well, in this case, what we know is that point right there, which is the y-intercept at 0, 5. And we can also count out the slope very easily. How do I get from this point here to this point there? Well, 1, 2, 3, 4, 5, 6 down. And 1, 2, 3, 4 to the right. So what are we looking at? We're looking at a slope of -6/4, which is -3/2. Now, we can go to point slope form, but like I said, if you have your y-intercept, that's really unnecessary. If you have your y-intercept and your slope, you're ready to go, because that's exactly what we're looking for. The border line will be y equals slope -3/2 x plus y-intercept. Now, if I didn't have my y-intercept, that's a different story. I have to go through point slope form to write this actual equation. But that's my border. The only thing left is, okay, what are you? Are you greater than? Are you less than? Are you greater than or equal to? Are you less than or equal to? Well, I can rule out two possibilities right now. It can't be those two. The reason being, that's a dashed line. So it's either greater than or it's less than. So again, I'm going to pick a test point, and I'm going to go with 0, 0. You go with this point 0, 0, ask yourself, is that going to be true or false in my equation? Well, 0, 0 is not in the shaded region, so I'm going to need a false statement out of this. When I plug in 0, 0, the statement needs to be false. So put in 0 for y and put in 0 for x. And I'm leaving this blank open for either greater than or less than. I need the statement to be false. So I have 0 compared to 5. Now remember, the origin cannot work. So I need a false statement. 0 being greater than 5 or 0 being less than 5. The answer is 0 being greater than 5 would mean that that origin would be false. So the final answer will be y is greater than -3/2 x plus 5. Little tricky, and you got to think in reverse when it's a false statement, right? But that's how you would actually write the inequality there.